Hello, start one again. Hello everybody, this is Naveen S. Sapare, Assistant Professor, Department of Mathematics, KLIT, Hubli. So in this class today we will discuss about the Z transform. In mathematics and in signal processing, the Z transform converts the discrete time signal, which is a sequence of real and complex numbers, in terms of a time domain representation. So the main use and main applications of this Z transform is in signal processing, and also it gives us the tractable way to solve linear and constant coefficient difference equation, Z transform. Now mathematically, how we will define the Z transform? So here the topic we discuss is Z transform. As a Fourier transform, this also have many applications in especially signal processing. So now mathematically, how we can define the Z transform? The Z transform of the function, Z transform of the function un is equal to f of n, where n is a positive integer, of a function un is equal to f of n is defined as zt of un. So we denote it as zt of un, that is representing the Z transform of un of the function un is defined as the summation from n is equal to minus infinity to plus infinity un into z raised to minus n, where n is a positive integer. So the summation of the product of the given function with z to the power minus n will give you the sequence, and if the sequence, the sum of the sequence or the sum of the series exists here, then we call that sum of this series as a Z transform of the given function un. But here what happens, n here un will be 0 for all the value of n less than 0. It means if n is negative, then definitely the function un will be 0. So then we define the Z transform of the function un as summation of un into z raised to minus n. Obviously when we find the sum of this series, the summation will be function of z. Okay, it is function of z. Then u bar of z will be called as the Z transform of given function un. Now let us take the important property of this Z transform. So from this property we will derive some standard functions, and also we find the Z transform of some standard functions. So what it is? It says that Z transform of n raised to k is equal to minus z into derivative of Z transform of n raised to k minus 1 with respect to z here. Okay, so this is the most important property. So it says that the Z transform of n to the power k is equal to minus z into the derivative of Z transform of n raised to k minus 1 with respect to z, where z is a positive integer. Now we will find out Z transform of some standard functions, and those functions are the basic functions. So we start with find z transform of k raised to n. So z transform of k raised to n. Obviously, to find the z transform of k raised to n, we are not going to use this first. We are going to use the basic definition of z transform. The basic definition of z transform is given as z transform of un is equal to summation from n is equal to minus infinity to plus infinity un into z raised to minus n. And since we know that un will be 0 for all the values of n less than 0, therefore I am going to use the summation from n equal to 0 only. So taking from n equal to 0 to infinity, in place of un I am having k raised to n into z raised to minus n. So therefore, simplifying here, summation from n equal to 0 to infinity, and this one can be written as k by z the whole raised to n. When you take this z raised to minus n in the denominator, it becomes z raised to n, therefore it becomes k by z the whole raised to n. Now expanding this summation starting from 0, when you put n equal to 0, it becomes plus 1. When you put n equal to 1, it becomes k by z. Next it will be k by z the whole square. Next it will be k by z the whole cube, and so on up to infinite term. And since we know that this series is representing a geometric progression or geometric series, so therefore the first term of this series is a equal to 1 and common ratio r is k by z. So we have a equal to 1 and r equal to k by z, where r is a common ratio of a GP, because this series is representing a geometric progression. Therefore, we have a equal to 1 and r equal to k by z. And since we know that the sum of infinite terms of a GP is given by a divided by 1 minus r, therefore using this formula we have z transform of k raised to n is equal to, it is a is nothing but 1 divided by 1 minus k by z. So this implies z transform of k raised to n is equal to, taking a LCM and simplifying, we have z divided by z minus k. So this is the first standard function, and the z transform of the function k raised to n is equal to z divided by z minus k, and obviously this one we can denote it as u bar of z also in general. So similarly we are going to find the z transform of the next function, that is 1. Okay, so now I am going to find out the z transform of 1 here. So what is the z transform of 1? Again I am going to use the definition. We know that z transform of un is equal to summation of un into z raised to minus n, and in place of un we are having 1. Substituting that value, and since we know that the function un will be 0 for all the values of n less than 0, therefore we will take the summation from 0 to infinity, and in place of un we are having 1, and in place of z raised to minus n as it is. Now simplifying this, here also we need to find out the summation of this z raised to minus n. So I will take that z raised to minus n in the denominator, and now expanding this summation starting from n equal to 0 we get 1, then when you put n equal to 1 we get n equal to 0 and n equal to 1, then n equal to 2, then n equal to 3, and so on we get summation up to infinite term. And since when we see this series we know that it is representing a geometric progression, so therefore here a is nothing but 1 and r is again 1 by z. So therefore again we have the same formula, the sum of infinite terms is nothing but S infinity is equal to A divided by 1 minus R. So using the same formula, we have Z transform of 1 is equal to 1 divided by 1 minus 1 by Z. Now taking a LCM and simplifying, we have Z transform of 1 is equal to LCM is Z, so we have Z divided by Z minus 1. So we have the Z transform of 1. So this is the second standard function. So we need to remember these all formulas, because when you solve the problems related to this, we are going to make use of these formulas. So these are two basic formulas. So Z transform of k raised to n is equal to Z divided by Z minus k, and Z transform of 1 is equal to Z divided by Z minus 1. Okay, now we derive the next standard function. So we'll find out the Z transform of next standard function. So let us take Z transform of n. So obviously Z transform of n means we can compare this n with this n raised to k formula. So we know that Z transform of n raised to k, which is a standard form. So Z transform of n raised to k is equal to minus Z into d by dz of Z transform of n raised to k minus 1. So we compare this n with this standard form, and we come to know that here k value is 1. So when I substitute this k value equal to 1 in this formula, so it becomes, so minus Z into d by dz of Z transform of n raised to 1 minus 1 is obviously n raised to 0. So n raised to 0 is 1. So we have Z transform of 1. So this is equal to minus Z into d by dz of, and since we know that Z transform of 1 just we derived, so Z transform of 1 is nothing but Z divided by Z minus 1. Now we need to differentiate this Z upon Z minus 1 with respect to Z here. So therefore we have minus Z into bracket, applying U by V formula, that is a quotient formula. So we have Z minus 1 into 1 minus Z into 1 divided by Z minus 1 the whole square. So simplifying further, we have minus Z into, so obviously it becomes Z minus 1 minus Z divided by Z minus 1 the whole square. So simplifying further, we get here minus Z into Z cancel, we have 1 divided by Z minus 1 the whole square. So simplifying it further, just multiplying this minus Z with the inside term, we have Z divided by Z minus 1 the whole square. So which is Z transform of n. So therefore Z transform of n is nothing but Z divided by Z minus 1 the whole square. Now we will move to the next function, finding the Z transform of n square. So again we compare this n square with this n raised to k, and obviously we know that k value is 2 here. Therefore substituting k equal to 2 in this formula, we have minus Z into d by dz of Z transform of n, because k is 2, 2 minus 1 will be 1, therefore remaining is n raised to 1. So simplifying further, minus Z as it is, d by dz also as it is. Now writing this Z transform of n, we know that Z transform of n just we derived it, it is Z divided by Z minus 1 the whole square. This is equal to minus Z. Now differentiating it, applying the quotient formula U by V rule. So we have here Z minus 1 the whole raised to 4, and here it is Z minus 1 the whole square, and derivative of Z is 1 minus Z as it is, and the derivative of Z minus 1 the whole square will be 2 times of Z minus 1. Now we need to simplify it further. So before simplify, definitely we observe that z minus 1 is common in this numerator. So taking that z minus 1 common from the numerator and cancel with z minus 1 the whole raised to 4, we have z minus 1 minus 2z divided by z minus 1 the whole cube, because we are taking z minus 1 common from the numerator and it cancel with the denominator. Simplifying further, we have minus z into bracket. Obviously, we have minus 1 minus z divided by z minus 1 the whole cube. Just multiplying minus z now. So we have finally z plus z square divided by z minus 1 the whole cube. So this is z transform of n square, and hence one more standard function. Similarly, we can derive one more standard form, the z transform of n cube. So z transform of n cube is equal to, again we find the z transform of n cube using the standard form. Z transform of n raised to k is equal to minus z into derivative of z transform of n raised to k minus 1. So obviously here k is nothing but 3, therefore the formula becomes minus z into d by dz of, it is z transform of n square. And since already we are having a z transform of n square, so substituting that, minus z into d by dz of, so z transform of n square is nothing but z plus z square divided by z minus 1 the whole cube. Now we need to differentiate. So minus z as it is, again applying the quotient formula u by v rule. So we have here z minus 1 the whole cube into derivative of z is 1 plus 2 times of z minus z plus z square into derivative of z minus 1 the whole cube. So it becomes 3 times of z minus 1 the whole square, whole divided by z minus 1 the whole raised to 6. So here bracket complete. Now before simplifying, try to take a common functions from the numerator every time. So obviously when you observe the numerator here, we come to know that z minus 1 is common in both the terms. So taking that z minus 1 the whole square common from numerator, remaining is z minus 1 into 1 plus 2z, and here z minus 1 the whole square we have taken common, so remaining is minus 3 times of z plus z square, whole divided by z minus 1 the whole raised to 4. It is because we are taking z minus 1 the whole square common from the numerator and cancelling with the denominator z minus 1 the whole raised to 6, therefore it becomes z minus 1 the whole raised to 4. Simplifying further, we have minus z into bracket. Now simplifying further, z into 1 is z plus 2z square minus 1 minus 2z minus 3z minus 3z square, whole divided by z minus 1 the whole raised to 4. Simplifying further, minus z into bracket. Obviously 2z square minus 3z square is minus z square. Z minus 2z minus 3z is minus 4z, and constant term is minus 1, divided by, we have z minus 1 the whole raised to 4. Simplifying further, just multiplying this minus z with the inside terms, we have z cube minus into minus become plus 4z square plus z divided by z minus 1 the whole raised to 4. So this is z transform of n cube. So That's the proof here.